Okay, this is lesson 11.1.1. We're on platonic solids. So far you've learned a few solids in the previous lessons. You've got the cylinders and you've got some prisms. And so we're going to take a look at a few more of interesting solids, right? So in chapter 9, you study the volume and surface area of three-dimensional solids such as prisms and cylinders. A cube is a special type of rectangular prism because each face is a square, so everything is the same, right? What are some examples of cubes you remember seeing? So some things that I found, and let me share with you, that I've seen around the house, right? So I've seen dice, or cubes. These are cube sugar. We probably don't see them as much now. And blocks. When my kids were young, I definitely see a lot of these, right? So these are just some common items that we see almost every single day that are cubes. Let's write down some of the common items, right? So we saw some dice. We saw some cube sugar. And we saw some children block toys. And of course, there are many other examples out there that you see, right? I think another good example is a Kleenex box, the square one that I really like because that's the only one that fits in my car. So yeah, I like those. Okay, all right, let's move on to part B. Find the volume and surface area of a cube with an edge length of 10 units. So volume is actually pretty nice. Volume is length times width times height. So you take the length of 10 times 10 and times 10. So it's going to be 10 cubed, which is 1,000 cubic units, right? So that would be for the volume. Let me zoom in a little bit. Now, surface area, if you look at this cube, there are 6 squares. So you would really take each of the squares and go 10 by 10, and there's 6 of them. So surface area of a cube is 6 times 10 squared, which gives me 600 square units. Okay. So remember, the flat side of a prism is called a face, the one that I just shaded in right there, as shown in the diagram above, right? And then the points where the edges meet is, notice a line segment where two faces meet is an edge. So the lines here are edges. And then where the two edges meet are vertices, vertex, right? Vertex is singular, vertices are more than one. So how many faces does a cube have? How many edges and how many vertices? So again, you know, use a box or use a Kleenex box or the cube to look at, the dice to look at an actual thing. So think about it, and I usually use a room to think about it, right? So how many faces? Well, in a particular room, you have the front and the back, you have the right and the left, you have the ceiling and the floor. So there's 6 faces. So 6 faces. How many edges? So again, if you use toothpicks to make them, you will see you need 4 on the top, and you need 4 on the bottom, and you need 4 to connect all those, like 4 pillars. So that's 4 times 3. That gives me 12 edges. Okay. And then how many vertices? Well, how many points? You can look in the picture here. 1, 2, 3, 4. 4 on the top, 4 on the bottom. So 8 vertices. Okay. All right. Moving on. So a three-dimensional solid made of flat polygonal faces is called a polyhedron. A cube like the one you studied on the previous problem is an example of a regular polyhedron because all the faces are congruent regular polygons and the same number of faces meet at each vertex. In fact, you find the cube is the only regular polyhedron with 4 square faces. But what if the faces are equilateral triangle? Or what if the faces are other regular polygons such as pentagons or hexagons? What type of solids is formed when 3 equilateral triangles meet at each vertex? When 4 triangles meet? When 5 triangles meet? When 6 triangles meet? Do similar tests for regular pentagons and hexagon. For each regular polyhedron, describe its shape and count its faces. So again, the idea is that you take triangles and you meet them at one corner, right? So if you take triangles, equilateral triangles, you notice I have 3 of them meeting at one point, and no matter how I turn this, it's 3 triangles at every single vertex. That's what it's talking about. It has the same number of the regular polygons meeting at each of the vertices, right? So each of them has 3. Okay. All right. So they gave you some ideas here. It's very, very hard to see this, but the first one has 3 triangles, right, at each vertex, but in total you use 4 triangles to make this shape, and you'll see in a minute how, right? So there's 4 triangles here. So I'm going to help you see this. This one has 4 triangle faces. This picture next door actually has 4 on top and 4 on the bottom. It has 8 triangle faces. This next one is weird. It actually has pentagons. So it has 12 pentagon on each face. And then this one actually has 20 triangle faces all together. It's very cool. All right. All right, so it says follow directions below for help in testing various ways that are congruent. Regular polygons can build regular polyhedra. Start by focusing on equilateral triangle. Attach 3 equilateral triangles so they're adjacent and share a common vertex. So I have 3 regular triangles, right, and equilateral triangle, and they are sharing a common vertex right here. Okay. Then it says fold and attach the 3 triangles so that they completely surround the common vertex. So I'm going to fold along these 2 lines, like it says so here. Okay, give me a minute here. Okay, crease down on my lines here. You should remember how to make equilateral triangles from our construction unit. So here's my triangle, and I creased it, and it wants you to fold until these 2 come together. So they meet up like so, right? So this is now my triangle. My pyramid, right? My pyramid without a bottom. My bottom is empty here. So really, if you look at it this way, this is the pyramid, right? This is the pyramid, okay? So how would you describe the shape? This is a triangular pyramid with no base. Nothing on the bottom. It's empty on the bottom here, okay? So now repeat your test to determine what solids are possible with 4 or 5 or more equilateral triangle. So you just draw another triangle, and then you try to match the 2 edges together again. So if you want to do this experiment with 4 triangles, you draw another one here, and then right here, and then you can take that and fold it with this one. You want 5 triangles, you just draw another triangle and then try to fold it together. It's actually possible. It's really cool. Okay, so a regular polyhedron is possible. Describe and state the number of faces it has. If a regular polyhedron is not possible, explain why not. So you can actually have 4 triangles together, right? 4 triangles at one vertex actually creates this one right here, right? Because each of the tip here has 1, 2, 3, 4, has 4 triangles there. So 4 triangles actually creates the 8 triangle faces. 8 triangle faces shape, which we'll talk about in a minute, okay? And 5 triangles, so 4 triangles. 5 triangles you can do too. 5 triangles, and this pattern is very weird. 5 triangles actually doesn't create 10. It creates this one right here, the 20 faces. Each tip here actually is created by 1, 2, 3, 4, 5 triangles coming together at one vertex. So that one is the 20 triangle faces. Okay, can you have more? And here's the trick. You can't have more. If you have 6 triangles, each triangle tip here, because it's an equilateral triangle, each triangle tip is 60 degrees. If you have 6 triangles, 6 times 60 is 360 degrees. It's a full circle. So you can't make a polyhedron. It can't be a circle there. Polyhedron has to have angular tips here. So it can't be a circle. So that's why it's not possible. So you can only have 3 triangles come together, or 4 triangles come together, or 5 triangles, but no more than that. So keep that in mind. What if the faces are regular pentagons? Try building a regular polyhedron so that each vertex is the intersection of 3 regular pentagons. So you can Google this, and I'll tell you how to Google it later, but you can Google and find these things, what we call nets, and it shows you, it gives you the base of how to make these shapes. So this is the one that's talking about. This is the one where it has pentagons, and it gives you these tabs so you can actually glue it together. But notice that every single tip, well, it's a little hard to see, but every single tip here, if you pull them together, you have 1, 2, 3, 4, 5. You'll have 5 pentagons. All right, so it'll be connected there. It's kind of cool. 5, 4. Let me think. No, it's 4. Actually, sorry, it's 3 pentagons. Miss Chu is getting a little bit confused. Yeah, sorry, I have to have a visual thing here. So you take 1, 2, 3 pentagons. It comes together at one one vertex. And again, sorry, the math will prove why it's true. Okay, so it says try building so that there's 3 regular pentagons it meets. So if it's 3 pentagons, it makes this last shape that we saw here, the 12 pentagon faces. So it creates the 12 pentagon face shape. Okay, can you make more? You cannot. Yeah, my mistake. You cannot make more. Why? Because if you have 4 pentagons, think about it. Each pentagon, the interior angle is 104 degrees, right? Sorry, 108 degrees. We learned that 540 divided by 5. Each interior angle is 108 degrees. If 4 pentagons, that will give 4 times 108. That's 432 degrees. That's way bigger than 360. It's bigger than a circle, so not possible. So we can't be 360 and we can't be bigger than 360 because then it's not a possibility. Okay, so end your investigation by consider regular hexagons. Can you have 3 or more regular hexagons at a common point? Well, think about it. Regular hexagons have an interior angle of 120. So 3 hexagons will be 3 times 120. That gives me 360. Same problem as part B here. So not possible. Okay, so I'm tired of calling it 8 faces, 20 faces, 12 faces. What are they called, right? So Plato, this is Plato, dude back all the way in 490 BC. Yeah, he's from a long time ago. All right, so he spread them about 2,300 years ago during the time of Plato, a Greek philosopher and mathematician. Polyhedra are classified by the number of faces they have. For example, a cube is a solid with 6 faces, so it can also be called a regular hexahedron. So it's numbered by the number of faces you have, right? So which ones do I have, right? So look at back on number 2 here. We have the 4 faces. That's a tetrahedron. We have the 8 faces. That is the octahedron. We have the 12 faces. That is the dodecahedron. And we have the 20 faces. And that's the icosahedron. So those are the ones we've seen so far. Okay, so again, let me show you something real quick. You can definitely Google these and see what they look like from a better view, right? So if you just go ahead and Google the names of these, like tetrahedron. So this is a tetrahedron, and hopefully you can see this a little bit better. Each of the vertices have 4 triangles. Each of vertex here has 1, 2, 3, 3 pentagons, right? This is the dodecahedron, and this is the icosahedron. So this one has 1, 2, 3, 4, 5 triangles at this one point, right? And again, you can definitely see some of these on Google. It tells you like all these shapes and the names of them, right? So yeah, we typically call this cube. We don't really call it hexahedron, but if you really want to follow the names of the Play-Doh solid, we can call it hexahedron, right? So if you want to see how these are made, you simply go on Google and look for net, like the one that you catch birds with. You look for net of tetrahedron, net of octahedron, and that's how I'm able to find all these pictures here. And you just cut and then put glue on these tabs, and the shapes will come around really nicely. So I have made here a tetrahedron that I was trying to show you, and I was able to make a very cool octahedron. So the octahedron has 4 triangles on each side, but with limited time, I do have dodecahedron at school, so I don't have it in my hands. And icosahedron, that would be my next challenge. All right, okay. So then it says, find the surface area of each Play-Doh solid you built in the previous problem. So, you didn't build this, but it wants you to find the surface area of each of these, of the 4 shapes we have, the tetrahedron, the octahedron, the dodecahedron, and icosahedron, right? So remember, for 3 of these, they're all regular, they're all equilateral triangles. So we can actually just figure out one equilateral triangle and multiply by how many faces we have, and that we will have the surface area. It's really a nice shortcut, right? So we know for a fact that the tetrahedron and the octahedron and the icosahedron are all made of triangles. So let's deal with that first, right? So a regular triangle or equilateral triangle looks like this. It says each length is 2 inches. Okay, so let me zoom in a little bit and remind you that, hey, when we make our height here, because we're trying to find the area, we simply cut this edge in half. So that's a 1. and this is 60 degrees, right? And this is a 30, 60, 90 triangle. So if that's a 1, this is root 3. So the area of this triangle is going to be 1/2 base. Base is 2. Remember, we cut it in half to figure out the height. And then the root 3 is my height. So if you simplify this, each triangle is root 3. So that makes it easy because now I have the tetrahedron, I have the octahedron, and the icosahedron. Right, this is the surface area of all of them. So surface area of all of them. So tetrahedron has 4 triangles. So it's 4 times root 3 is 4 root 3, right? And then we have octahedrons, 8 of these. So 8 times root 3. And then your icosahedron is 20. So 20 root 3. And these are in inches. So square inches. Right? So, you could multiply these out and get the decimals, but these are the exact answers. Okay, so what about my icosahedron? Well, my icosahedron is made of a pentagon, so I need to figure out the pentagon first. So remember, pentagon is 5-sided, right? And the way we find these is we make our triangle and remind ourselves that, okay, the given information is this is 2, but I am going to figure out my height by cutting it in half. So my height, and this is 1. Each interior angle of a regular pentagon is 108 degrees, which means this angle here is 54 degrees. 108 divided by 2 is 54. Okay, so I use SOHCAHTOA. Tangent of 54 equals opposite over adjacent. So I simply figure out tangent of 54 to find my height. And my height is approximately 1.38. So the area of one triangle is 1/2 base of 2, again, remember base is 2, right, times the height of 1.38. So multiply it out, you get 1.38. And now the area of a pentagon, or this pentagon, is 5 of these triangles. So 5 times 1.38, which gives me one pentagon to be about 6.9, right? Okay, so now for us to figure out the icosahedron, so surface area, no, not icosahedron, the dodecahedron. Surface area of dodecahedron is equal to, there's 12 of these, so 12 times 6.9, right? 12 of these pentagons, so 12 times 6.9 is about 82.8 square inches. Okay, so these were my answers for the 3 of them, and that's my answer for the last one. Let me zoom out for you. Okay, that's it, guys.